So what we'll do next is put in some numbers into that equation and run through an example calculation based on the well-mixed room model. So let's do a quick calculation. So let's assume that there is a room volume of 200 cubic meters and an airflow rate of 20 cubic meters per minute. And so what it means is that there are 6 air changes per hour for this room. So let's take a brief moment to discuss this term ACH, or air changes per hour. So what we are saying is that if we have a room of volume 200 cubic meters and the airflow is 20 cubic meters per minute, or in an hour, which has 60 minutes, we'll have 1,200 cubic meters of airflow per hour. And so in 1 hour, there's 1,200 cubic meters of air moving through it. It means that the air in this room has been completely changed over 6 times, because the airflow is 1,200 divided by 200 cubic meters. So we are left with 6 air changes per hour. So a new batch of 200 cubic meters of fresh air comes in, and then another batch of 200 cubic meters of fresh air comes in. And so there are 6 such air changes occurring in 1 hour for this room. So that's basically what is meant by air changes per hour. And this is a unit that you will encounter frequently in indoor air calculations. So coming back to our calculation, we start at time 0, and we assume that G, the generation rate, is equal to 1,000 milligrams per minute, and it's constant with time. And we will also assume that the supply air contains no contaminant vapor, so Cn is 0. There are no vapor removal mechanisms other than exhaust air, so Ks of L is 0. And we are also going to assume now that at time t equal to 0, the concentration in the room is also 0, so it's a perfectly clean room. And so we want to find the equation for Cs of t. So we plug in all our values of G and Q and V for our equation. And so we end up with this equation that is on the top. So Cs of t is equal to 50 times 1 minus exponent minus 0.1 times t. So how did we get the 50? If we go back to the generation rate, that is 1,000 milligrams per minute, and the ventilation rate is 20 cubic meters per minute. So 1,000 divided by 20, that is 50. So that's the value of G divided by Q. In the exponent, we have minus Q over V. So Q is, again, 20 cubic meters per minute, and the volume of the room is 200. So we get Q over V as 0.1. So we see this nice graph. The concentration starts at 0 at time t equal to 0, and it increases with time, but then it flattens out and eventually reaches an asymptotic value of 50. And that is the final concentration in the room. So let's again spend some time thinking about the physics of what's happening in the room. So we start off with a clean room, so the concentration at t equal to 0 is 0. And now as contaminant starts being added to the room because of the generation process G, the concentration in the room is increasing. And you can see that at, in the beginning part of the curve. So there is a steep increase. Air is still moving, so there is clean supply air, which is now also cleaning the room, but there is not that much contaminant in the room to be cleaned out. And so the increase in concentration is mainly being driven by the generation process. But then as enough contaminant molecules enter the room air, now the cleaning mechanism actually shows its effect. So we can see that the rate at which the concentration is increasing in the room is decreasing. So we can see a gradual bending of the curve. And so what this means is that the contaminant removal mechanisms are also now beginning to have a significant noticeable effect. As we go further and further in time, the processes that are adding contaminant and removing contaminant are getting more and more in balance. And then finally, we reach a point asymptotically when the contaminant adding processes and the contaminant removing processes reach a balance. And at that point, the concentration cannot increase beyond 50 milligrams per cubic meter. At that point, the room concentration reaches what is known as steady state condition. And we can now go back to our initial equation before we made our simplifying assumptions about Cn and case of L being zero. So if the in-room emission rate is constant, G, and emission continues for a long time, the contaminant concentration in the room will reach a steady state value CSS for steady state. And this is G plus Cn times Q in the numerator and Q plus KL times V in the denominator. So we can apply that equation to our example where we have the Cn is 0 and Ks of L is 0. And so we arrive at our value for the steady state concentration, which is 1,000 divided by 20, or 50 milligrams per cubic meter. There is another part of this more general equation that is very useful. So let's assume that the room now has an initial concentration C of 0. And now we'll assume that there is no contaminant emission into the room. So G is now 0. And we also assume that there is no contaminant in the supply air, so C of N is 0. But the air is still moving through this room, so there is clean supply air, which is now exhausting out of the room as well. And so since G is 0, if you recall the overall equation, the first term, which has that coefficient of G divided by Q, that is now 0. And we are now only left with the second term, which is the exponential decay term. And so C of T now reduces to C of 0, which is the initial room concentration, times our exponential decay term, and the constant within parentheses is Q plus KL times V divided by V. And since we are assuming that Ks of L is 0, this equation traditionally appears in textbooks and other references as C of 0 times exponent of minus Q over V times T. Now, using that purging equation, we can run through a quick calculation. So let's consider the same room as in the previous example with a volume of 200 cubic meters and an airflow rate of 20 cubic meters per minute or 6 air changes per hour. Now let's also assume that the initial vapor concentration C of 0 in the room is 50 milligrams per cubic meter. But now the generation source is cut off, so G equal to 0. And the concentration in the supply air, C of N, is 0, and there are no other vapor removal pathways other than exhaust air, so K of L is 0. So we want to find the equation for C of T, the concentration in the room air, when there is no source generating contaminant in the room. We plug in our C0, our value of Q, and our value of V into our equation, and so we get this equation. So C of T is 50 times exponential of minus 0.1 times T. And we can plot this in an Excel spreadsheet. So at time T equal to 0, the concentration is 50. And as time increases in value, the concentration decreases and it reaches an asymptotic value of 0. So this is pretty intuitive, that if you have no source generating contaminant, but only room air flowing through it, then the room is eventually going to be purged of the contaminant. And so this equation is called the purging equation.